Hello. Welcome to Mr. Powers Teaches. Is this statistics? Probability? Algebra? Geometry? I don't know. It's probability. We're doing some probability. And just as a quick review, we talked about what's independent events. And I did bring that up because in my thinking that we were going to do these kinds of things, probabilities of unions of two events. And what's a union of two events? It's pretty much an or. And so again, I just want to reiterate that probability of two events, E union F, is the same as probability that E or F happens. So probability I draw a king, then or a queen. That would be like if E is probability of drawing a king out of a deck of cards and F is a queen, then it's the same thing as saying probability I draw a king or a queen. Saying the same thing as probability of the union of those two events. U stands for union here, this weird U, that without a tail, as an or for the most part. And then we have intersection of two events. That is like an and. So if I say, what's probability I draw a queen and a king, you think that would be a smaller thing, smaller probability, right? And you would be right. It's much smaller when we're talking about and, because that means that they have to happen at the same time. If we're talking about an and, those have to happen at the same time. Okay, and we're very picky on that. So I made the point last time also that, let's say you're at a restaurant and the waitress says, you want soup or salad? I would say, yes, I want soup or salad. And then she would wait for me for a while. I'm like, okay, I'll take the soup, because that's not what she meant, right? But if it's a logical statement, question, or means it's one or the other or both, right? Either way. If I wanted both of them, it would be a yes. If I wanted one or the other, it's a yes. But for and, when we're talking about ands, it's do you want both? Do you want soup and salad at the same time? It's like, so I would say no if I only want soup. Say nope, I do not want soup and salad. Then she should follow up with, well, do you want soup? Then I could say yes or no. She'd be able to figure it out from there. Which brings me to this really fun comic. Maybe if I have time at the very end of this video, I'll show you this fun, stupid math comic titled Three Logicians Walk Into a Bar. It's a fun little joke. Okay. So that's what we talked about. And then we were able to talk about independent and dependent events. See, so if we have independent or dependent events, it doesn't matter. This is our formula for actually, let's do it like this. This is our formula. So we'll just copy and paste. Oh, great. Hold on one second. This is our formula for finding the union of two events, or like an or statement. And so yeah, we talked about that last time. So anyway, let's try to do a problem that contains an or an and, a union or intersection. And see what we can see. So in a certain Algebra 2 class of 28 students, 14 of them play basketball and 17 of them play baseball. Now, something you got to think about right now. 14 plus 17, what is that? That's 31. That's not 28 students, right? What does that mean? That means there's some students that play both. They play both sports, right? Okay, so that's something you got to keep in mind, right? Because the probability is the number of things we want or the number of ways to get what we want over total possible outcomes. Okay, so there are 9 students who play neither sport. So now we can see there's actually a lot of overlap because there's 9 that don't play any. What is the probability that a student chosen at random from the class plays both basketball and baseball? So in this kind of a situation, I actually like to use something called a Venn diagram. And so we're going to set up a Venn diagram here so that we can figure out the right probability. So we can figure out how many students, because what are we trying to find? How many students play both basketball and baseball. So if basketball is E and baseball is F that they play, this is kind of like that probability of E intersect F. Who plays both? Who plays basketball and baseball? Or we could say P of E and F. Okay, so who plays baseball and basketball? Okay, if E is play baseball or basketball and F is play baseball. Okay, so that's what we're trying to figure out. So let's make a Venn diagram to solve this issue. Okay, so this is the way we're going to do it. Big circle for, we'll say, basketball. Since I already used E, I'll say here, this is E. Here, we'll write it in here. E is in here, okay? And then we're going to have another circle. It's a beautiful circle. This will be F. And then we got to have a rectangle around, oops, it's a terrible rectangle. There we go. Rectangle around the whole thing to represent everything else. Now we know everything else. Everything else is they don't play either one. We have 9 students there. So we can put a little 9 there. Actually, let's use a different color for the number of students in each one. So there's 9 here. 14 play basketball. So we know there's 14 in E. But we don't know if it's split up, how much is here and how much is in here, right? So let's we'll put a 14 here for now, but we know there's overlap. And there's 17 that play baseball. 17 that play baseball. Okay. How many are in E and F? Let's do it that way, right? How many total are in E and F? That's a very important thing to know. Let's see if we can figure it out that way. So how many are in E and F? So, well, it's 28 total, right? But we know in E and F, that means they play a sport. 9 don't play a sport, right? So we can subtract 9. And what we get, yes, that's right, Michael. What we get is, 19? Play a sport. All right. Great. So we know there's 19 total in here, right? So now what? What are they asking for? Oh, so we actually don't have to figure out who plays. No, we do. We want to know who plays both basketball and baseball. So now what do we do? Okay. So, real quick recap. 28 students total. 9 don't play sports, so 19 play sports. But if I add up the number of students that play basketball plus the number of students that play baseball, I get way more than 19. So that is completely unacceptable. What do we get? We get 14 plus 17 is 31. We get 31 students, but we should have just 19 left because there's 28 total. So what does that mean? That means some students were double counted. How many students? Well, that's easy. We know 19 play sports, not 31. So let's minus 19 from here and see what we get. We get 12. So that means 12 were double counted. That means there's 12 that are in both. That's what it means. So let's fix that. So if 12 were double counted, that means there's 12 in the overlap. There's 12 that play basketball and baseball. Okay. So that means if there's 12 here out of the 14, there's actually only 2 that only play basketball, and that would live in here. And if 12 out of the 17 do both, there's only 5 that only play baseball. Now we can easily double check and make sure this diagram does represent our situation. If we add them all up, we know what the total of our population that we're talking about is 28. So 9 plus 5 is 14, plus 12 is 26, plus 2 is 28. Perfect. We got it. Now we can easily find a probability. We want a probability of E intersect F. That's where they overlap. That's the overlap here. That's who plays both at the same time. And that's another nice thing about Venn diagrams is it helps with that language. It makes it real obvious that the and the intersect are the same. It kind of shows that in a way. So now that I know that, we can do our probability. Because what's probability? It's what we want out of the total. So P of E intersect F, probability they play basketball and baseball is 12 out of 28 students total. And then, of course, we can reduce that, divide by 2. I get 6 out of 14, divided by 2, 3/7. And I'll be done. That's my answer. Piece of cake. Now, I do have a question, though. I presented a formula earlier. This guy. I wonder if we could have just solved that more quickly. Now, the thing is, too, and maybe we can also talk about the double counting, because we had the double counting in here, right? That minus, but this was for the or. So we could mess with it, though. Let's see if we can mess with this, because we were trying to find this, right? We're trying to find probability of E intersect F. So you know what? It's kind of fun. If we're dealing with events that are not mutually exclusive, that is, if you're in one event, you could also be in another event. They're not mutually exclusive things. Then we have to worry about this double counting. Similar to when we have dependent events, like one event will affect the other, okay? So that's just some terms we didn't talk about before, but mutually exclusive events are events that, one thing has nothing to do with the other. Here, just because you're in one group doesn't mean you can't also be in another group, right? So here we go. If I solve for this, I would add probability of E intersect F to both sides. And then I would subtract this guy from both sides at the same time. So minus probability of E union F minus probability of E union F. And we could get a new formula. And that formula would be probability of E intersect F is probability of E plus probability of F minus probability of E union F. So I don't know. Is that a handy formula? It's something we could do. We were given probability of E and probability of F. Here, P of E is 14 out of 28. Or, could just use the counts. Here, F. Oh, actually, yeah, basketball and then baseball. And then here's P of F. 17 out of 28. Okay. 9 students who play neither sport. So how many play a sport? We figured that out. It was 19. So that means we could write that also. Probability of E union F was 19 out of 28. Okay, so we have all these pieces. Does that work? E was 14. F was 17. And E union F was 19. Now, yeah. Play one or another. Yeah, it was 19. Okay. All right. So that means, yeah, and that's actually exactly what we did, isn't it? 14 plus 17 is 31 out of 28 minus 19. And we get 12 out of 28. So that's a really fascinating thing, is that if we want to be lazy and just use a formula like this, or like what we wrote down in green here, this guy, we could have done that. All right, so that's just something that's nice to take a look at and see. Yeah. And but I do prefer to diagram it out. I think it's kind of more fun, it's more intuitive. But by diagramming it out and then looking at the formula, you can see how the formula works and why the formula works, right? Because if I wanted probability of E intersect F, you think about it, E intersect F, this formula works, right? I'm sorry, E union F. If I know the rest of these, it definitely works, okay? Because once again, this will be the last thing and this will be the end. This is a long video. Probability of E was 14. Probability of F, 17, of course, out of 28. Minus the intersection. So minus the intersection. Well, the intersection was 12, right? We had figured it out. 12. Because we got to subtract that 12. We couldn't just do 14 plus 17 because 12 were in common. So when we add 14 plus 17, we're adding 12 twice, the ones that were in common in both groups. So that we want to avoid the double counting. That's why we subtract the intersection here. And that gets us a probability of E union F, which we were given was 19. We were able to figure that out, was 19. So that's where that comes from, okay? So hopefully that's all making sense and that this example was helpful in solving problems like this. So that's all I got for you. Until next time, enjoy doing math.